This is Corey Delano. Hello, this is my video on doing the solve a combined spectral problem. My group is 21, and listed here, the molecular formula is C10H14O. So we want to start this process by calculating the degrees of uncertainty, the du, which is going to be 1/2 the hydrogen saturated minus the number of actual hydrogens minus halogens and nitrogens. We don't have any of those in our formula. So let's solve for the number of saturated hydrogen. So that's going to be 2 times the number of carbons plus 2. So we have 10 carbons, so it's going to be 2 times 10 plus 2 is going to be 22. So we're going to plug that back in up here, and then again it's C10H14O, so the 14 is going to go here. So that's going to look like 1/2 times 22 minus 14, and that is going to be equal to, this is going to become 8, so this will become 4. So we can plug that into the worksheet here. So degrees of uncertainty is going to be 4. Again, we have C10H14O. Okay, so now we want to move on to looking at our IR spectrum. And we want to look at the most important points here. So this big drop down here looks like it's below 3,000. So we can say that, I'm going to say like 2,900. And we can say that that's going to be an sp3ch. Then some other things that I'm looking at, there's kind of some noise happening here, which I believe is the aromatic region. And that kind of makes sense with our molecular formula and degrees of uncertainty. So already we can be thinking that we might have an aromatic. So I'll just say like 1,700 to 2,000. It's like aromatic. And then right about here, we see at around 1610, we have some noise happening here. And we can say that that's going to be a alkene, C to C double bond. So now that we have that out of the way, let's move on to the carbon 13. So we have 1, 2, 3, 4, 5, 6, 7 points on the carbon 13 spectra. And let's write down where they end up. So I see 24-ish, 32, these are all estimates. 57 would be here. Next is going to be 114. Then it's looking like 128, 141, and 158. So then we kind of want to line these up with their ranges of what type of bonding environment it's going to be. So 0 to 40 is just going to be sp3. So these first two are sp3. And then 40 to 90 is going to be carbon to oxygen. So that's just the 57, it looks like. So C to O, and that's sp3. Okay, next segment is going to be 90 to 160, which is all of the rest, and that is going to be alkene or aromatic. Okay, so finally we can go on to the last step. And there are 1, 2, 3, 4, 5 peaks happening here. So let's figure out their chemical shifts integration and multiplicity. So the first one we have is approximately 1.24, and then that is a 6H, and then it looks like there's only 2 peaks here, so that's gonna be doublet. Okay, so the next one is here. I'm gonna say it's like 2.85. It's 1H, and it looks like there's 7, so seplet. And then the next one is here. It's gonna be like 3.8, let's call it, and it's 3H, and it's looking like a singlet. And then these two over here are like 6.9 and maybe 7.4. And it looks like these are going to be both 2H and both doublet. Okay. So finally, we want to move on to the interpretations here, and then we can predict our structure. So if we have 6 hydrogens that have a doublet, and they're at 1.24 parts per million, we know that they're sp3, and to me, this suggests that there's going to be like 2 CH3s attached to a carbon here that's also attached to something else, because that would make all of these hydrogens doublets. So that's gonna be like 2 sp3s CHs, and that's gonna be connected to another CH, like coming down here. So 2.85 here is gonna suggest that we have an OCH group, and it's sp3. 3.8 is gonna suggest the same thing. And then the 6.9 and 7.4 range is both going to suggest aromatic. Okay, so we kind of have 3 things going on here. We have the aromatic, the single bond to oxygen, and this group here. So I'm going to start by drawing the aromatic ring. And then I'm going to connect this to one part. Yeah, so all of these H's are doublets. And then I know that we're going to have an OCH group, and for now I'm going to put it just opposite. No, this is going to be a CH3, because the 3 H's need to have a singlet, so they need to be connected to the oxygen here. And then the rest of the doublets are going to be here. And it looks like that all works out.